In this episode, we are going to do an infinite world with an object-oriented design. So let's start with a little recap of what this series is about. We are implementing the same problem over and over again, and with different ways so that we learn different things from each solution. A recap of the rules is that we are implementing the game of life, which is played on an infinite grid, and each grid can be either alive or dead. And then we are doing iterations with each state of our world with different living cells. We have a set of rules that define how the next world will look like. If a cell has less than 2 neighbors, it's going to die. This is the loneliness rule. If a cell has exactly 2 or 3 neighbors, it's going to stay alive. And if a cell has more than 3 neighbors, then it's going to die, and that's the overpopulation rule. And finally, we have the spawning rule. When we have 3 neighbors and the cell itself is dead, then it's going to be alive in the next generation. So in this episode, we are going to do an infinite world, as I promised before, but also I will try to make it as object-oriented as possible. So let's get started. I'm gonna start by writing a simple test for the game of life. And unlike before, this time I'm going to first concentrate on how we interact with the board itself, and I'm not gonna start out directly writing tests for the rules. So I'm going to specify that an empty world has that 0, cell. And as this is object oriented, I'm going to create first a game object. It's going to be a game of life object. And of course that also already fails the test because we don't have a game of life class. Now we have one. Next we need to go back into this test and write the isAlive function. So we expect a function called isAlive, and this will return false in our case, but I first have to pass in the coordinates. Now I could just like last time pass in 2 zeros, but since we want to make this object oriented and the cell is kind of part of the domain, why don't we just create a cell object and pass the 0 to that? That way it just looks better. So now it's a failing test again. We don't have a cell class, so let's create it. And also we don't have an isAlive function, so let's create it. And now all we have to do to finish this test is to expect this isAlive code to be false. And also like here we have the expect function which is not defined. That's why it shows up in purple. So I'm going to import expect from expect.js. And then this is a failing test. The way we fix it is by returning false here. Okay, so now we established how we ask for a cell if it's alive. So, but of course we also need to be able to spawn cells. So we specified that 0 cell can be spawned. And then we also need a game object, of course. And on this game object we are going to call a spawn function, which will expect a new cell Now, of course, this is a failing test now because we don't have a spawn function. Let's create that function. There it is. And then, of course, we also need to expect. So I'm going to copy this line over here and just change this to true because we expect it to be alive once it's been spawned. Of course, it's a failing test. So how can we fix it? Well, initially this should be false, and then once spawn is called, then it should be true. So the easiest way to do that is just create an alive field here that is false by default. Return that alive. And here in spawn, we are just going to take this alive and turn it into true. And then if I call the spawn after that is alive is going to be true. Now this is of course cheating, because if I create a cell 3-5 then with spawn, then is alive will return true for everything, not just the 3-5. So we actually have to specify that a 3-5 cell can be spawned independently of 0-0 cell, and I can type. Okay, and here we go. So it's going to be a very similar test to the previous one, but this time I'm going to spawn the 3 and 5 cell and check if 0-0 is false. And of course that test is failing. And the way I'm going to fix this is that I'm going to make this alive into an object. And if it's an object, then I can just turn one key on it to true. So we are going to have the key cell as the key, and then we put true in there, and then in that case we can just say like this. Problem is that if this is not defined, then it's not going to return false, but it's going to return undefined. So we are just going to do a double bang here so that the undefined turns into true and then it turns into false. Essentially this is just casting the undefined into a false. So, but this doesn't work yet. The reason it doesn't work is because cell is not it's not a hashable thing, so we still have to make sure that JavaScript understands when a cell is identical. So what I'm going to do is I'm going to turn this into a field and also this into a field, and we don't need that there. And once these are fields, then I can create a toString function that will just return, and I'm going to do a template string here for this x comma this y. Actually I'm even going to put those in parentheses, and then it works, right? Because what happens now is that we get the cell, and when we put it into this square bracket, then it turns into a string, and basically we are indexing with the strings. So that makes sure that only the cells that are actually alive are going to, for each of the actually alive cells, we will have a true here. Now this, here you might have the question, why do I use an object and not a set? And the reason is that with set, that's not as easy to do this little trick of defining toString and having that as the key. But I still feel uncomfortable with this being like this is kind of primitive obsession. We have logic in here that has nothing to do with the game of life itself. It's about how we store the data. So I'm going to separate this out into a class called game of life board, and I'm just going to copy this whole thing over, and instead of having an alive field here, I'm going to have a board, which is going to be a new game of life board. And I'm just going to, first here, I'm going to delegate this column, this board dot spawn cell. So this, now actually both this alive thing and the game of life board have the same cells inside them. And once I have that, then I can just replace this line with return this board dot is alive cell. And now I have delegation, and this alive thing here is not necessary anymore. Oh wait, what happened? Yeah, because we don't need this. Okay, so now we have cleaned up, we have refactored here. Another refactor I want to do is here, because these tests are getting a little hard to read. So one thing that we notice that we always need a game of life object. So how about we just create that up front, and before each of the tests we are going to initialize that with a new game of life. That's it. And now I don't need these lines anymore. So let's clean this up. That's it. Another thing that's kind of disturbing is all these new cell things here. Like it's a nice interface, but how about we just take these two parameters here, and I'm just going to extract this into a function on this abstraction level, and it's going to be just a cell function, and then I can align that and that. Now of course I'm kind of annoyed that it didn't switch those over, but let's do that manually. Also, this can become more like const cell, and like this. It's a cleaner way to phrase it. Okay, so we have this. I don't need the return either. So we have this now, and now I can just take this, do a simple replace with the new cell 00 to cell 00 replace all. Oh, unfortunately I had a minus sign there that wasn't supposed to be there. Alright, so now if I run the tests, it's good. And also, like, this doesn't read very well. Expect game is alive cell and so on and so on. What I actually want to write here is expect dead cell 00. It would just sound much nicer. So how do I do that? Well, I can create a constant expect dead, which will be a function, takes a cell, and then it's going to be this expression here with just a cell here. Okay, so now I can just replace this whole thing with that shorter line, and then that's kind of establishing a really nice DSL for phrasing our tests going forward. similarly here, we also need the whole thing for alive. So I'm also going to define expect alive. The only thing that's different is that this is true. And then what I can do is replace this line with basically something like this, but for is alive or expect alive. Okay, and for the last test we can also replace this with an expect that. Okay, so now we have a really nice DSL for phrasing or tests. We have the basic data structure that's of course an infinite row, because we are just storing the alive cells as coordinates and hash it with a simple hash function, which is in our case to string. Now all I have to do is start writing tests for the actual rules. So let's do that. So last time we started out really quick because we tied our solution to a specific way of representing the world. This time we had to first establish the relationship and how we communicate what cells are alive. So then next we specified that empty world has that 0 cell after being evolved. Okay, so basically we have this very simple test here, and I'm going to just change it very slightly. I'm going to add game.evolve here, and that's failing because the evolve function doesn't exist. So I have to create the evolve function, but this evolve function is going to be empty for now. Game.evolve, and evolve isn't a function. Oh, because I put it in the wrong place. This should go in here, sorry. Okay, now it's passing. And that was fairly easy because that basically just established that we have an evolve function. So the next is going to be a bit more interesting. We are going to specify that lonely cell 0 or lonely 0 cell dies when evolved. Okay, so this is the first case where evolve actually changes something, and we are going to spawn that 0 cell and then evolve the game, and then we expect a dead cell there. And that's failing because we spawned the cell and evolve doesn't do anything. So how do I fix that? I fix it by just saying that this board, well, it's going to be a new game of life board, and then it's empty, so we are back at green. Now the next interesting test case is when something actually survives, right? So we need to specify that that the 0 cell with 2 neighbors, I'm going to use -1, -1, and -1, 0 as our example. stays alive. Okay. Alright, so now we just take the previous test again and just duplicate this line twice and just add -1 here and -1 0 here, a bit of formatting, and we expect this to be alive, which it won't be. So how do we fix that? Where we can go back to the evolve function. I'm going to just extract this into a variable for now. It's going to be the next state. And if this dot board is alive, and just like with last time, we are just going to check if the cell -1 is alive. And if it's alive, then I'm actually going to go ahead and on the next board spawn the cell 00. Again, that fixes the test. But of course, this is not entirely correct, because now even if just the -1 is alive, then we keep 00 alive. So the next logical test is the test before this one, logically, is a cell with single neighbor. -1 dies. And I just have to remove this line and change this to that. So of course, this is very similar to our previous solution, where we again had to check if the other cell is also alive. And at this point, like this expression, what it says is that this specific cell and this specific cells are alive. So there are two cells that are alive. And we want to generalize this. And of course, this here can be turned into a function for now, so that it's easier to manipulate it. And this function is going to be, no, actually, let's not create the function yet, because for now this is just returning true, right? So what I want to do is first make sure, convert this into an actual calculation of neighbor count, and then after that extract it. So I'm actually going to just convert this true or false into integer, 1 or 0, based on whether it's true or false. And here as well. And now I can, instead of and, I can just add them together and check that it's exactly 2. And this actually works. The only thing is I need triple equals, yeah, okay. And now I can extract that function that I wanted to extract a second ago, which is the count neighbors. And now I can go ahead and refactor this even a bit more, because if you think about it, like here we have we have that -1 cell and the -1 0 cell, but everything else is the same twice. So how about we rephrase this slightly and say that this is actually just 2 cells and x -1 y -1, and then another little object x -1 and y 0, and then I can just use a map, and that map will take this delta. So because what I'm driving at here is, is that these are going to be our deltas, and we are going to add those to the central cell. So for each delta, I'm actually going to create the new cell delta x and delta y. And then once I have that new cell, I'm going to map that further. Actually, now I'm going to just filter, because what I can do now is I have a cell, and I can just take that cell, put it into this dot board, or actually it's just this is a live function because it's being delegated. So we have this cell, this is a live cell, filtering, so that will remove all the cells that are not alive. And then we actually get an array that has the length equal to the number of alive neighbors. Well, as long as we agree that these two are the neighbors, which we of course don't, but for now we can actually do that. And then I'm just going to return this thing instead of this expression. So that was a nice little refactor of the previous phrase, and it's much more readable. We just take the deltas, convert them into cells, filter out the living cells, and just to get the length of the living cells array. Nice. Okay, so next step. So now we have that. Yeah, so next step should be to just extend this array with the remaining neighbors. And how can I force that? The way I can force it is just writing a second test for this, essentially. So we could just write the second test, which would be -1 and 1. And then here we change this, and we expect the same thing. And of course it's failing. So I can go back here, and I can just say x -1, y, and 1. And you see that this kind of, we kind of have to keep repeating this, so why don't we refactor a bit? And the refactor that I'm going to do is that I'm going to just take this cell out of here, this cell -1, 0, and also, and then just do a for each on it. Actually, we need a parameter here. Actually, no, it's going to be the neighbor cell, sorry. Because cell is also the function name, and I don't want to shadow that function with our local variable, so neighbor cell. And then I can move this thing inside of here and just put neighbor cell here. And because neighbor cell has a toString function, I can actually turn this into a template string and just put neighbor cell here as well. And it's going to be casted into a string and show up as we expected. Okay, so the next step is, of course, like, I want to unify this test with the previous one. So let's do this and remove this, and now we have the same number of tests, just this one, is now has a data provider. And now I can just add more cells to the data provider, and I'm not going to go back and forth because it just doesn't make sense. I'm just quickly going to add that 5 extra tests that we need now. So here for 0 and 0 minus 1 0 1, and also like here we have the 1, and here 0 and 1 and minus 1 here. So these are the remaining tests that we need to write, and of course now it's gonna fail 5 tests at the same time, but we know how to fix them one by one. So I'm just going to go here and just fix them one by one. So the first one is 0 and minus 1, and then we have still 4 tests. Then we have the 0 and 1 case. We are down to 3 tests. I can just take this whole thing here, paste it in here, remove the minus 1s, and we have all the tests fixed. Okay, so now we actually can count neighbors. This is almost a complete implementation of the count neighbors. It's almost complete because it only works for 0 0 for now, but we are going to come back to that. And here we actually have this working for count neighbors equals 2. So the next logical test is going to be when we have 3 neighbors and we survive. Okay, so let's look at that. And basically here 2 neighbors minus, yeah, I'm actually going to write again specific examples. So 3 neighbors minus 1 minus 1 minus 1 0 and minus 1 plus 1, and it stays alive. I actually need to add those 2 new cells. So this one is 0 and this one is 1, and this should be alive, and it's not. So the way to fix it is going back into our evolve function. I'm gonna extract this into a variable count and just do an OR here. Okay, so there are multiple ways we could continue this, but maybe the next nice step would be to add again the case where we count neighbors 2. We also spawn this cell when actually that cell is dead. So we actually shouldn't spawn a cell when the original cell is dead. So I'm going to say specify that this is dead 0 0 cell with 2 neighbors, and just an example here, I don't know, 0 minus 1 and 1 1, whatever, states that. Now I just take 2 lines from here, minus 1 0 minus 1 and the 1 1, and I'm going to evolve that, and once I evolved it, I expect that the 0 0 cell is dead. So I actually have to go back and say that here we have like if count equals 2, then we also should check that that is alive and new cell 0, 0 is also alive. Okay, so that's nice. But now we should start writing the tests for the non-zero zero cells, right? But before I do that, I do want to do a bit of refactor, because for now here we just have this cell 0, 0, and the count neighbors doesn't depend on it at all. So I'm actually going to make our lives a little easier by doing a bit of refactor by passing this in here. And since this is also always 0, 0, I do not add behavior by actually going ahead and adding in the cell .x and the cell .y here, because all of our this doesn't add behavior because it's always 0 for now. And this is going to come handy when we write the next test, which is specify that cell okay, so let's say that 3, 5 cell with 2 neighbors phones. Actually, I don't even add the specific neighbors here into this test because it's not that important at this point. Here it was important with the 0, 0 because we were writing many tests for the same case, but now we established the neighbors, so it's not really necessary anymore to specify which neighbors, and it's not in the test's name. So we are going to spawn cells, for example 2 and 4, and 2 more, 3 and 4 and 4 and 6. Okay, so these are 3 neighbors, none of which is 3 and 5. And oh no, let's first start with 2 neighbors stays alive. So now I kind of got confused. I don't want to have the spawning rule first. I want to have just a staying alive rule for 2 neighbors. And I'm going to change this to 3 and 5. So now we have 3 cells, one of which is the 3 and 5. We are going to evolve this whole thing. And we are going to expect that it's alive, cell 3, 5, and it's failing. And this is why it was useful to just pass in the cell and add this little thing here, because now we would have to edit anyway. Because what I need to do now is just duplicate this whole thing. I don't need to create the count once again. And I just go in and change all of these to 3 and 5. And that's it. So this is code duplication. I can go ahead and refactor it. And the way I'm going to refactor it is, again, I create an array with the 2 specific cells that I want to check. This one and this one. Okay. And Then I can just do for each and move this whole thing inside of here, and then I don't need this anymore. Yeah, I actually have to add the cell here, and cell, and cell, and cell. Okay, so now it works. A bit of refactoring again. I kind of feel that this here is actually something we can extract into a function called should be alive. And yeah, that's not really how I wanted to extract it. First, let's extract it into a variable then, alive, and then take these two lines, extract that to should be alive, and now I can inline this one and this one, and now it's pretty clear that actually what we need is just filter out the cells that should be alive. So here I'm going to do a filter cell, this should be live cell, and do the for each on the filtered array, and that way I can remove this if statement here, which is just looks nicer, and it's actually not that big of a difference. Still, it's a lot nicer. Just have to keep removing stuff. Can I join these lines? No. Okay. Alright, so this is actually a pretty clean thing now. And of course this is just very specific for now. So I'm going to write one more test. Actually, it's just to force more generalization. So instead of 3 and 5, let's say -2, 8. Again, -2, 8, and -1, 7, and -3, 6. And then I'm gonna check -2, 8. So this is again failing, and the reason it's failing is because we don't have here a generic term for the cells that could be alive. So what I can say is just take from the board, I'm going to create a list function, and that list function is going to list all of the cells that are inside. And the way I'm going to do that, for now we are actually like putting true in here, but it doesn't really have to be true, it could be the cell itself. And if we do that, then now I can say object values and just take the alive cells from there and just return this. So this way we can now return all of the alive cells in this list. Great. And now what I have to do is take here, instead of having this array, I can just say this dot board list, and that's it. Alright, so that's still failing a test. Why? Oh, obviously So my test wasn't correct because here I said like minus 2, 8, and I wanted to have neighbors, and this is not a neighbor. This is a neighbor, and that fixes this one. Okay, and yeah, of course, now I feel bad because I changed the code when the test wasn't correct. Anyway, now it's actually working, and it feels like we are done, but there is a catch, because now if I were to remove this here, sorry, here there should be a, yeah, oh, I see why. Okay, so if I remove that phrase, it still passes, because we are actually only looking at the cells that are alive, and that actually broke our spawning rule. So we actually have to find a way to get that functionality back. How do I get that back? Well, I actually should have, in this list should also list the neighbors, because actually the cells that are alive in the next generation are not the ones, not among the ones that were alive in the previous one, but those who had alive neighbors. Because for something to be alive, it either has to be alive itself and have neighbors, or it should have exactly 3 neighbors. So all of the cells that are alive in the next generation are cells that had neighbors. So what we could do is to just take this list and replace it with all the cells that have at least 1 neighbor. How do we do that? Well, for that I actually come here and do a bit of refactor, because here we are calculating all of the neighbors of a specific cell, and we will need that. So what I'm going to do is I'm going to take this part of the code, and just this part, and move that into the cell. So I'm going to say cell.neighbors, and I'm going to put this on the cell. It's a nicer structure anyway. And then of course this cell becomes this, and this one becomes this. So actually this had kind of had feature envy anyway, because we were basically just using the cell, and now it turned into this. That's actually nice. Feels more object oriented. And now that we have that, then we will be able to use this function in a second. I forgot to return. Okay, before adding new code, always run the tests, because like a second ago when I changed this code here, I didn't run the test after refactor, and guess what? I screwed up the refactor. So now it's working, and now we can get back to writing that test that I wanted to write a second ago. But I also noticed a bit of inconsistency here, that and wasn't necessary, and this should be not a template string anymore. Yeah, no other inconsistencies. Just run the test, and now I can duplicate this one, and like the only change is that this is a dead cell, and instead of staying alive it's going to spawn. And then I don't have to spawn this here, and it still should be alive, and that's failing. And then, as I said before, we want this list to become the list of neighbors instead of the living cells itself. And the way I'm going to do it is I'm going to do a flat map. So flat map, if you don't know, takes the array, maps all of its elements into an array. So we would have, if you would have map here, let's first write map. If you had math here, then we could say that for each cell, let's take the neighbors of that cell. But this would be an array of arrays. And what FlatMap does is that it flattens this out. So it takes all of the elements of the outer array and just puts the items in there into the array itself, and that way it becomes a flat map, a flat array, not an array of arrays. And now our tests are passing, and that's it. This is a complete solution. We have the board, and we just take the list of living cells, map it into the list of cells with some neighbor, and then we filter out the ones that should be alive, and for each we spawn the cell in the next generation. Now, of course, this feels weird that everything is so functional here. We are using this functional interface, yet we have this variable here. So let's turn this into a proper reuse. And the way I'm going to do that is the next is going to come in here, and this new game of life board will become our initial value. And the trick that I'm going to do is that I'm going to make sure that spawn actually returns this. So it becomes a nice little fluent interface that way. And then we can just say that we reuse and just go through and all of the cells and spawn whatever is necessary and just return the result. Actually, it should not return but override board with this thing here. Something is wrong, right? So we use, oh yeah, because we actually don't want to add the return this here but into the board. And that's it. Now we are done. So the only thing that is kind of tricky here is that if you think about it here, when we list the living cells and then map it to the neighbors of the living cells, we will get the same cell multiple times. And then we go through and filter them out, and we still have the same cell multiple times, and we still spawn the cell multiple times. That feels inefficient, but this really doesn't matter, because all it does is that we are going to spawn multiple times and it's still going to be alive. And we could filter it out, the duplications, but doing it would actually cost more than the extra cost of spawning multiple times. So for now, this is the solution we go with. In a following video, I will do a different solution where we get to a solution where we don't have that problem, and we actually look at every cell only once. But that's for another time.